Hi, so I will be presenting on the paper Effects of Lower Surface Ocean pH upon the Stability of Shallow Water Carbonate Sediments. So just some background information. As you'll know, as atmospheric carbon dioxide increases, it tends to lead to a decrease in ocean pH, and you can kind of see how that's occurring right here. As H2O interacts with carbon dioxide, it forms carbonic acid. That carbonic acid will break down into bicarbonate and a hydrogen ion, and that bicarbonate can further break down into carbonate and another hydrogen ion. Another thing to note is that carbonic acid can actually interact with calcium carbonate and form a calcium ion and the bicarbonate. One thing to note here is that will not form a hydrogen ion and therefore not decrease the ocean pH and therefore act as a buffer. Some of those carbonate minerals that can interact with the carbonic acid include calcite, aragonite, and high magnesium calcite. The one we'll be focusing on in this paper, or the one they focused on in this paper, is the high magnesium calcite, which is actually extremely unstable. The goal of this paper was to determine the effects of ocean acidification on the surface ocean by using sediments. So the methods: sediment was taken off of 2 sites off of Lizard Island in Australia, and you can see it right up here. It's off the northeastern shore of Australia. It's a really small island. And what they did is they took those sediments and they wet sieved them in order to determine the sediment size, as well as they found the proportions of calcite, aragonite, and high magnesium calcite using X-ray diffraction analysis. Water was also collected from Australia, and what they did is they treated it in order to remove any form of organic compounds, and they performed titrations to determine the amount of bicarbonate and carbonate in that water. One last thing they did is they did a tank setup. So what they did is they took that water, put it in a tank along with 1 centimeter of sediment, and sealed it off in order to prevent any form of air-water interface reactions. And they put a CO2 injector and a pH sensor in order to kind of control the pH. And every 1 to 3 hours, they took some of that water and tested it for magnesium and calcium ions. So here are the results from the mineralogy. So the most important thing to note for the mineralogy here is that Coconut Beach has a large amount of high magnesium calcite, meaning it has a large amount of the unstable calcites, while Lizard Head has aragonite, which is much more stable. In addition, Coconut Beach is predominantly composed of smaller sediments, as you can see over here, while Lizard Head is predominantly composed of larger sediments up here. So these 2 figures are showing, figure A is showing Lizard Head, while figure B is showing Coconut Beach. The pH is on the x-axis, while alkalinity is on the y-axis. And the important thing to note about the y-axis is when it is above 0, dissolution of the calcites is occurring, while anything below is the precipitation of those calcites. So you can see here at Lizard Head, which is the aragonite-rich sediment, you could see that precipitation is occurring pretty much at any pH, even at the much lower ones. Coconut Beach, on the other hand, once the pH hits 7.8, that calcite starts to dissolve almost immediately. And keep in mind that this is the calcite that is the high magnesium calcite, therefore making it much more unstable. It also has a much smaller grain size when compared to Lizard Head. However, previous studies have disproved that there is any form of correlation between grain size and the dissolution. Another thing to note is that in those water samples, they found that there were unexpectedly high levels of magnesium ions when compared to the calcium ions. So this figure here, you can see a bunch of different experiments were run, and the white bars are the expected calcium ion levels, while the gray bars are the actual amount that was measured. The black bars are showing the magnesium ions. And as you could see, the measured calcium ions in the water was much lower than the expected. And what they actually found was happening was when that high magnesium calcite ions were being dissolved, they would actually reprecipitate into low magnesium calcite, which is much more stable as opposed to the high magnesium. So what's happening is the magnesium ions are entering the water, while the calcium ions are entering the water and then immediately being taken away and forming the low magnesium calcite. So the major conclusions of this paper is that the high magnesium calcite, when it dissolved into that low, or dissolves and then reprecipitates into the low magnesium calcite, it can actually act as a buffer to prevent ocean acidification. And this is really good because it's going to prevent ocean acidification. However, this leaves organisms that use the high magnesium calcite extremely vulnerable to ocean acidification, as that essentially their calcite source is just dissolving immediately. And this includes organisms such as the coralline algae. Thank you so much.